On August 6th, the hallways of Frederick Reines Hall at UC Irvine stirred, as they always do, with the sounds and sights of science and scientists. One of those scientists, Allie Zito, who's a Ph.D. student with Professor Jenny Yang in the Department of Chemistry, made her way to her lab. Where inside, one of the first things you see are metal and glass boxes that hold the kinds of chemicals that need to be held in metal and glass boxes. Rubber gloves reach out from the boxes like the arms of someone trying to escape from another dimension. Glass beakers hang from the walls, and you feel like you're somewhere where a language is spoken not just with sounds, but with reagents and bubbly things. It's here that Zito, in that language, works to pull planet-warming carbon dioxide straight out of the air.
I'm working on carbon dioxide capture and concentration. So what that means is taking carbon dioxide out of the air around us or straight from an industrial power plant which has a little bit more carbon dioxide by concentration. And what I'm trying to do is make a CO2 supply, a feedstock. There's a lot of work going into CO2 reduction, so taking carbon dioxide, making something else out of it, methanol, formate, things that can be used for other uses. And what I'm doing is making that CO2 supply, making that feedstock. What I want to watch is I want to see the brown or the dichloromethane layer on the bottom and then my water layer on the top. What I'm interested in is my dichloromethane layer that has my chemical in it, but there are probably some impurities that are in the water layer. So, though it looks pretty well separated, I'm going to shake it a little bit, let off any bubbles. Shake it, let off any bubbles, and as I place it back, we should be able to see some nice separation form. So currently there is technology out there to capture carbon dioxide, but it's not efficient. It uses heat. So there are molecules out there that can grab onto carbon dioxide, but to let it go, to concentrate it, it takes a ton of heat, which is a ton of energy, and it's super inefficient and just not realistic. What I'm trying to do is make it more realistic. I'm trying to use electrochemistry. So trading electrons, sort of using electricity to our advantage. I am making molecules that work like an on-off switch. Most of the time they're off. They don't want to grab onto carbon dioxide. But I can activate them, I can turn them on using electrochemistry. When I toss electrons at them, suddenly they're on. They want to grab carbon dioxide, but when I take electrons away, they're done. They don't want any part of carbon dioxide.
At UCI, there's a program called Solutions at Scale, which aims to support projects like Zito's, which, though confined to her fume hood for now, could one day be one of the tools used to help reduce CO2 concentrations in the atmosphere.
The work is going to ideally be scalable someday. I'm in a collaboration with some theoretical chemists at UCLA and some engineers at MIT. And what I'm doing, my part in this, is designing that molecule that can turn on and off easily while being cool in the presence of water and oxygen, which not all molecules are actually. So my part is to make a lot of this molecule. Then I'm going to send it off to these engineer collaborators, and they're working on making a system that is capable of capturing the carbon dioxide and releasing it in the real world.